Hello everyone, let us solve the GATE mechanical questions of 2009. So a property that cannot be obtained from a tensile test. So you understand about tensile test, right? So we have a tensile specimen. Wait. Okay, so you have a tensile specimen which looks somewhat like this. Okay, and we apply a force for the elongation. So through that we can find this Young modulus also, yield strength we can find, UTS also we can find, because we get a stress strain curve, right? So from here we can get everything, but this endurance limit we cannot obtain because this is a property which is tested in the case of fatigue, right? So fatigue, it is tested somewhat like this. Okay, so like sigma A and number of cycle, it tells you that at what number of cycle basically if you apply that much amount of stress, so below that stress basically it will not fail. Okay, next, a defect that is bounded by two mirror plane. Okay, so basically a defect that is bounded by two mirror planes, so somewhat like this, if you see, and the plane of symmetry will be like a mirror, so you can that is basically called as twin, right? Because the grain boundary, it is somewhat different. Stacking fault, it is different. Okay, stacking fault, because of arrangement fault, it is in the edge dislocation, this is again somewhat different. Okay, then match the loading conditions in group 1 with the characteristics in group 2. Okay, so when we do the loading of any material, so what is the characteristics that is formed? So in the case of tensile, okay, so basically it will form like a cup and cone kind of a structure, right? Basically this will form for a ductile one, so it is given for here I am assuming for a ductile case. The compressive, when we do the compressive, like we have the specimen, we do the compressing, then what will happen in the middle, it will be somewhat like bulge, it will form, so that is not called as barreling. Then in the case of fatigue, we understand it is form of, it contains striations, right? Then creep, so creep we also understand it is forming intergranular cracking, like so, because it is happening at higher temperature, so this will match with option B. Next, a unit dislocation with a Bezier vector B1 will dissociate into two partial dislocations with Bezier vector B2 and B3 if and only if. So we know that energy, okay, we know that energy in the reaction side should be greater than the product, so that's why it will form, because to decrease the energy, right? So it will form under only condition, I think it should be first it is P, right, in the terms of energy, so it is there. B1, this is incorrect, and this is B1 equal to B2 plus B3, so vectorially this should be also consistent, right? So P and R should be the correct answer, so option A will be the correct one. Next, during a sheet stamping, so we have a sheet and doing the stamping means putting some pressure, it is observed that sheet surface area triples, so this is the initial area, that is A0, and this gets tripled to your AF, and that is equal to 3 times of A0. Okay, so the true thickness strain, so we need to measure the thickness strain. Okay, so thickness strain basically epsilon T we know, understand, and it is telling you true, so true we measure by LF by LI, right, or ln TF means final thickness minus TI, right? So now so we understand that area the volume should be constant, so A0 into T0 should be equal to AF into TF, so TF will be nothing but A0 T naught by AF, and AF we know it is 3 times, right? 3 A naught T. So the final thickness it will be decrease such that it becomes T naught by 3. So it becomes L naught. So T naught by 3 into T naught. So it will be ln 1 by 3, that is nothing but minus ln 3. So if you find this ln 3, okay, let me check what is this ln 3. Do you have the calculator? Okay, let me arrange a calculator, then after that I will tell you. So ln 3 is 1.098, so we can consider minus 1.1, which is your option A, right? Next, high stacking fault energy, high SFE, plays an important role in determining the work hardening ability of a metal. In this context, the correct logical sequence is, so high SFE, that means lower gap between the stacking faults, right? So lower gap means easy movement. So high HFE, easy cross slip, yes, it will be there. Then lower work hardening. So I think option A should be correct, but let us see option B, C, D also. High HFE, difficult cross slip, no. Low SFE, easy cross slip, no, right? Low SFE means higher gap. Then low SFE, difficult cross slip, okay, yes, it is correct, but low work hardening, this is incorrect, right? Because if difficult cross slip is there, then work hardening should also be greater, right? So option A is the only correct answer. Next, a 3.0 mm diameter single crystal, okay, so this is 3.0, D is equal to 3.0 mm, is loaded to force equal to 400 Newton along O1 direction. So let us assume this direction O. The resolved shear stress on 111 plane, right? So 111 plane means the normal should be your 111 and your direction it is giving 1 bar 0 1. Okay, so I think everything it is given. So the resolved shear stress is, so resolved shear stress means the component of this stress on this direction, right? Okay, so basically if you see the formula, then that CRSS equal to sigma times cos theta cos lambda, right? So we assume theta over here, then lambda over here, right? So let us find this cos theta and cos lambda, and this sigma we can find by sigma, that is force by area, right? So cos theta and cos lambda. So F it is nothing but 400 and area will be equal to pi d square by 4. So pi into d, d is 3 mm, so 3 into 10 power minus 3 square by 4. So this is giving you the stress, okay? And cos theta, so cos theta it will be like this vector, this dot product of like 111 with 001 divided by root 3 and root 1. So it will be 1 divided by root 3. Then cos lambda will be this 001 dot product 1 bar 01 divided by root under 1 root under 2. So it will be again 1 by root 2. So it will be 1600 divided by pi into 9, and this will be like ampere. So 10 power minus 6, that is 10 power 6 I will consider, so it will be ampere, then 1 by root 6. So let us find this value. So it will be 1600 divided by 3.14, okay, divided by 9, then divided by root under 6. So I got 23.1138 MPa, right? So this is matching with option C. So this will be your answer. The stress applied on a material is, okay, so this is your stress. The maximum shear stress experienced by it is, okay. So this is the basically, in the form of 3 by 3 matrix. So it is already given the principal diagonal values, right, and the other values are 0. So you can consider these 3 values as the principal value. So sigma 20, sigma 2 is equal to 21, sigma 3 is equal to 21, right, because we needed to assume it as sigma xx, sigma yy and sigma zz, but since the other values are 0, so we can consider this as principal stress. So tau max is nothing but sigma 1 minus sigma 3 by 2, so it will be 0, right. Match the properties in group 1 with the testing techniques in group 2. Okay, so electrical conductivity, how can we check? Jomini test we do for what? To measure the hardenability, right? So okay, so we can do the matching from group 2 to group 1. So let us see, Jomini test for hardenability, I think it is not given over here. Okay, ISO test to find the impact energy, right? Then dilutometry. So dilutometry, it is used for thermal expansion. Then 4 probe technique, okay, leave it right now. Then DSC, differential scanning calorimetry, so it is used for specific heat. Okay, so now this P will match with 4, so P matches with 4, Q matches with 2, R matches with 3, so R matches with 3 and S matches with 5. So this is option D, question number 47, and this will be answer D, right? Okay. Next, a metallic rod with 2 into 2 mm square cross section is being tested in tension and has the following mechanical property: Young modulus, Poisson ratio, then yield strength, work hardening exponent, UTS. The rod is loaded to 1000 Newton. The magnitude of transverse strain is, okay, so this is your specimen, okay, and the area of this specimen looks like this, 2 into 2. So area will be nothing but 4 mm square, right, 2 into 2. Now this is loaded to this 1000 Newton. The magnitude of transverse strain we need to calculate. So to calculate the transverse strain, right, so strain in this direction, right, sigma basically y, this is epsilon y and epsilon x. So what is the relation between epsilon y and epsilon x? So epsilon y is equal to minus times of mu times of epsilon x. This is the relation, right? So now to find this relation, we have the mu, but this elongation in the x direction we don't know. So we will calculate. So how that can be calculated? That calculated because stress is given. So at that stress, what is the strain? Because that may be in a linear in the elastic region. So that will give that, okay. So this is in the elastic region. So we can directly use the Hooke's law, right? Now to find this Ex, we need to do the hard work. So for that, we need to first find the stress what is applied over here. So 1000 Newton divided by this 4 mm square. So 4 into 10 power 6 meter square. So 1000 divided by 4 is nothing but 250 MPa. So 250 MPa is the stress, and we can see that yield stress is at 500 MPa. That means it is lying in the elastic zone, right? Easy. This is 500, so it will be somewhere over here. So at 250, so the formula is sigma is equal to capital E, that is the elastic modulus, into epsilon. So this okay, and Young modulus, it is given 100. So we can find this Ex is equal to 250 divided by 100. Okay, so it will be like, I think, 2.5. Okay, 2.5, and this will be in GPa, so 10 power 3. So 2.5 into 10 power minus 3. Okay, so this is the strain in the x direction. Okay, so now once we get the strain in the x direction, so we can find in the y direction, that is sigma y is equal to minus times mu is 0.3 into 2.5 into 2.5 into 10 power minus 3. Okay, so it will be, do the calculation, 0.3 into 2.5, so it is minus 0.75 to 10 power minus 3. Okay, so since it is already given that we need to find the stress in transverse direction, that means it will be in negative, that is for sure. So epsilon y is nothing but 0.75 into 10 power minus 3. So if you do the calculation in percentage, so 0.75 by 1000 into 100, so it will be nothing but 0.075. Okay, percentage. So option B is the correct one. Now next is the modulus of resilience of the material. So modulus of resilience is nothing but half into the area, initial area, that is, right? So it will be half into this, you can say, like, stress into this strain value, right? So up to that point the elongation should be there, right? Or so sigma into E, and this E also you can find like sigma by E, so we can find sigma square by 2E. So sigma, we know it is 500, then 2 into E, that is 100. So it will be easy comparatively, right? So 500 into 500 divided by 2 divided by 100, but this is 100 in GPa, right? So we need to we will write here like 10 power 9, and here 10 power 6 it will be there. So 10 power 6 the power 2, so that means it will be 10 power 12 over here. Okay, so it will be like 1250. Okay, 1250 into 10 power 3. So we can write it as 1.25 into 10 power 6 joule per meter cube. So nothing but 125 megajoule per meter cube. So option D, right? So like this you can solve the questions, and it will help you for your preparation. So thank you all.